of duckweed. And the model itself can't predict if wind will sweep the duckweed off the pond or not. We can model a pond with duckweed, we can model a pond without duckweed, but we can't model if the pond will have duckweed or not, if you catch my drift. And this slide kind of summarizes a few additional challenges. So if you have a storm event, how much duckweed gets flushed out of the pond? We don't really have, so that's a lost term for the duckweed. It probably depends on, the details of the pond outlet and how big the pond is and so forth. I talked about the wind, and then we really don't know what happens to duckweed over winter in these ponds, and therefore it's challenging to set the initial condition in spring for the duckweed. And that, I think that's maybe one of the main reasons I can't really predict interannual variations very well. So, I'm almost out of time here, and I have a few conclusions. So, the pond hydraulics are, relatively easy to measure and to model, and they're sort of the baseline that you need if you want to do any water quality analysis for the pond. I will add that this whole groundwater component, groundwater interaction or infiltration, can be important and is a little trickier to get at than storm flows. Oxygen and nutrient dynamics in ponds and wetlands are really complicated because you start to throw in algae and other biology into the mix and a lot of chemistry. So we really needed a lot of field measurements in this project to have any hope of getting a reasonable model put together. And once you have a pond model put together, you can use it to study the response of ponds to climate change or changes in loading or management strategies. And in fact, management strategies is what we were focusing on this project. And John Gulliver will be talking about some of those results tomorrow, I believe. But the other point I wanted to make here is that just the process of putting together the pond model and figuring out what the important processes are and what data we need to calibrate the model really, I think, adds a lot of understanding to the overall, it adds a lot to the understanding of how ponds operate. And it can help guide what field measurements should we be focusing on in the future? What are we missing that's important in these processes? So that's, I think, another value of doing pond modeling. I think that's it. Like I said, we've had several funding sources, including the Local Road Research Board, MnDOT, and the Stormwater Council. Thank you.
No, I think two more speakers. Oh, that's right. We're switching gears here to from research to application with Mike McKinney, who is a senior water resources engineer at Bar Engineering. He is talking about modeling, design, retrofit, and repeat practical aspects and considerations in pond design. Thank you, Michael.
Thanks, Keith. Get the presentation loaded up here. Everybody, fun to see a bunch of familiar faces in the audience. While I'm opening this up, I'll just quickly introduce myself. My name is, as Keith said, Michael McKinney. I'm a practicing engineer at Bar Engineering Company. Got about 13 years of experience, a lot of which is designing and thinking about stormwater ponds, much like many other people in the audience today. I'll pull up in the agenda here and let you take a look at that while I kind of just blab away for a second here. So when I was first approached to present this morning, I was asked, okay, we want to hear about an engineer's perspective on stormwater pond design. So what that means is, what tools are engineers using to design ponds? How do engineers incorporate emerging research into pond design? And then, of course, what are all the other things that come up that take us from, well, here's our great concept for this pond, but the realities of regulatory constraints and internal dynamics of the project can really change things and impact what actually ends up going in the ground. So, that's a pretty broad topic. And I think further compounding the difficulty of this presentation is appreciating that we have such a great audience here today with people with amazing research backgrounds and people with years and years of experience in permitting regulation and municipal staff and watershed district staff. So my goal today is to do a pretty high level overview of all things that are kind of come into the engineering design of stormwater ponds, with the goal of helping people who, maybe you've got a lot of experience in, application of stormwater ponds, but a little bit less in monitoring and the other sort of constraints that impact stormwater design. So just trying to provide a high level overview to help people kind of fill in the gaps and provide some of the background that I've had in stormwater pond design in the metro area. So why ponds? We had some great discussion early this morning on, there's a lot of regulatory drivers that are pushing us away from stormwater ponds and pushing us more towards infiltration BMPs and filtration BMPs. But stormwater ponds are here to stay. A lot of the stormwater pond designs that I've personally been involved in have been retrofit projects. So we've got a stormwater pond that we want to improve the performance of, so that's going to remain a stormwater pond. In addition to some of these other niche case uses like, irrigation and reuse, that's a great application, potentially for designing a pond. But I also find that some of those co-benefits that have also been talked about today, like rate control and flood mitigation, those are some of the things that ponds are really good at, and especially when they're developed in areas that are hard to develop for other reasons. So some of those co-benefits like rate control and flood mitigation, aesthetics, recreation, habitat, things we're all aware of, are additional really important co-benefits that sometimes direct us towards stormwater ponds. So a quick overview of the key design elements. This is going to be really basic for some people in the audience, but when we're asked as an engineer to design a stormwater pond, first thing we need to know is we need to know the drainage area so we can estimate the runoff and the sediment loading that gets to the stormwater pond. That information then informs the bathymetric storage. We've got to make sure we can actually settle out the particulate load that we want to settle out, and we want to make sure that bathymetric storage doesn't fill up so quickly that we're going out there and doing sediment management every 5 years. And finally, we need to design the live storage. So live storage, to me, that's everything that's above the permanent pool, kind of up to the overflow elevation. So that includes designing your outlet structures to meet whatever your goals are, right? Rate control goals, flood mitigation goals, things like that. So again, those are the key kind of elements. And the next slide's, again, providing the highest level overview. This is not meant to be a pond design 101. This is more just an overview of these are the tools that practicing engineers actually use to calculate and determine these things that we need. So drainage area, that one we've got great tools for. So typically what we're doing as engineers is we're bringing in a digital elevation model into a geospatial program like ArcGIS Pro or CAD. And we're bringing in storm sewer data, and we're delineating that drainage area, and that's something we can do very accurately. Runoff loading, so once we've generated that drainage area, we now need to know, well, how much runoff is going to be generated from rainfall that falls on that. We all understand this. We got to know something about land use there. So fortunately, nowadays we have great access to data that provides information on land use. So typically anywhere you go in the United States, you're going to be able to find data sets that are publicly available and tell you something about land use, imperviousness. You can then bring that into a model, such as P8 or HydroCAD, to then estimate, using curve number method and green app method and a number of different hydrologic models, how much runoff is conveyed from that land use. So once you've estimated your runoff loading, you then need to figure out, well, how much sediment and pollutant loading is associated with that runoff. And I think this is where it really kind of opens up the can of worms if we're getting into things that we're not as good at as practicing engineers in terms of we don't always have the best available information. So this table, it's probably small text, from sort of left to right is kind of outlining some different methods that practicing engineers will use to actually estimate that sediment and phosphorus loading. So the simplest method is actually using what is very creatively called the simple method of routing and pollutant loading. It's basically you've got an annual rainfall volume, you assign a runoff coefficient to your different land use types, and then you assign an event mean concentration of your different pollutants to different land use types. That we've got great guidance in Minnesota on what to apply for those EMCs that is very research based, and that's great, but of course it's an estimate, right? This is not measured data. Maybe one step more complex is the sort of middle column. That's where we're actually trying to do physically based modeling to estimate this. So what I'm referring to there is we're actually going to try and model the buildup and wash off of sediment on a surface, and then of course actually model how those particles are filtered out or settled out in a stormwater detention basin. So the most common model that's utilized for that purpose, at least in my experience, is P8, which is a physically based model that actually models those particulates. And you might be saying, okay, well that's great, but how do you actually come up with the parameterization to run those models? Well, if we don't have monitoring data, we have to rely on default parameterization. And fortunately, we've got, as we heard about this morning, we've got great, the NERP study is kind of built right into P8. So if you've got nothing else to define your assumptions on, you can say, I'm going to select NERP 50th percentile. So this is just sort of an average urban area from that study. And it'll give you sediment parameters, and it'll give you associated pollutant parameters for that default assumption. And you'll hit run on the model, and you'll get a number. So that's great. We still don't know exactly how accurate that is. So with both of these methods, we're introducing uncertainty, and that's where we kind of talk about the art of stormwater pond design. We have to use other methods to kind of deal with that uncertainty that we're introducing through parameters that we're going to just be less certain with on a case-by-case basis. So obviously, the furthest you could take this, as we just heard, is actually doing the monitoring, right? So continuous flow monitoring, event-based pollutant monitoring to get your sort of event-based mass loading. It's really difficult. We'll talk more about that on some upcoming slides, and very rarely available. Sort of last thing on just how we actually calculate pond performance is, so now we've got the sediment and pollutant loading to the pond. So now, how much does that pond actually remove via settling? So if we're talking about a physically based model, we're actually modeling those particulates. So we've got a settling velocity for the 80th percentile of particulate, and if that is, if you compare that to the overflow velocity of the pond and the retention time in the pond, you'll figure out which particles actually settled out in that pond versus which particles just flew right through the pond and did not get removed. So that's how a physically based model would handle this. A more simplistic model, something like the MIDS calculator, an MPCA annual based model, they are using empirical relationships to estimate performance. So you'll plug in, okay, here's my permanent pool volume, and here's my live storage volume, here's characteristics of my drainage area, and a tool will say, okay, based on what you told me, I'm going to go to a lookup table, and I'm going to say, this is a type 3 stormwater pond, so therefore you get 90% TSS removal, and you get 60% total phosphorus removal. And again, these are all things that are based on studies and have a lot of information to back them up, but we have to just appreciate that these are estimates of pond performance. So you might be asking yourself, geez, if these are really important parameters, maybe we need to be doing monitoring to collect this information. I think a really key takeaway here is the reality is that is really difficult to do, and I think that's maybe driven home by, if you wanted to go out and do a monitoring project, you're probably going to need to collect 1 or 2 years of data, and that monitoring project is probably going to be more expensive than the engineering and design cost of the pond itself. So you need a lot of time, you need a lot of money, and a lot of times those things you're just not going to line up, or you're going to be able to go and collect that data to inform a one-off pond design is going to be incredibly rare. And we'll talk about more how we deal with that and think about that in upcoming slides. So finally, kind of moving on to bathymetric storage design. We've talked a little bit about this, and we've seen some really great figures and dynamics of settling in ponds, but ultimately, there's a couple of key design goals. We want to have a certain amount of detention time to remove that particulate that we want to be targeting. We want to review sediment management, right? We want to make sure that we're not going to need to go and do a dredging project because this pond's going to fill up 4% per year. So that's a consideration. Depth has historically been an important design consideration, in which, if you look at the Minnesota Stormwater Manual, it say, well, if you're less than 8 feet deep, that means you're gonna not have stratification and you're gonna have a fully mixed pond. Well, we just heard that that's not exactly the case. Even shallower ponds can have stratification and can have that sort of internal loading that results from stratification. So design guidance is kind of in flux, and it's something that we are, working on dealing with in our engineering and design applications. Again, the most basic, highest level estimate for if you're designing your bathymetric storage, if you look at the Minnesota Stormwater Manual, it'll say you need 1,800 cubic feet per acre. That's a half an inch of runoff from your watershed. That's maybe a good kind of starting point. Slightly better would be to attempt to estimate your sedimentation volume loss per year. So if you have a mass associated with what you think is going to be removed in that pond, you can convert that into a volume using a wet bulk density, and you can say, okay, I think this pond is going to fill up 1% per year, and I'm okay with that. That means I will go in and do a sediment management project once every 25 years. And of course, most rigorous and accurate is you do the monitoring to support those sort of design decisions. And again, just to point out, for a one-off pond design, you're very unlikely it's going to be that you're going to have that monitoring data to support that design. And this is just one of your go-to sort of consulting. You've got this triangle of cost, schedule, and scope, and you get to pick two. So usually that means that you're just not going to have the time and you're not going to have the budget to actually do the monitoring to support design. Last element of just basic design is the live storage and the outlet design. Goals here are highly variable based on the specifics of your pond. I put the basic requirements from the construction stormwater general permit. I find that oftentimes the watershed district rules or WMO rules are going to be even slightly more restrictive. So a lot of times you're kind of more in that sort of other example goals that's at the bottom of the slide. A lot of times regulatory considerations are going to drive your live storage design, in that a lot of times you're going to need to meet rate control requirements. So you can't exceed existing condition rate control. That's a big one that often gets pulled into pond design. But then there's also, flood mitigation. Maybe you're trying to retain the 10-year flow so it doesn't actually overflow from the basin. Channel protection, trying to reduce velocities for channel forming flows, and water quality goals. So lots of different things can guide your live storage design. And I won't get into this too much, but when we're actually designing those outlets that we've seen, we've talked about complex outlets. A lot of times, maybe if you have a really simple flared end section type pipe, maybe you can use simpler models like HydroCAD and P8 to do the pond design. Oftentimes, we have a little bit more complex situations happening where maybe there's downstream tailwater impacts and a lot of things to consider. So in those cases, you might need something more like a fully dynamic unsteady state model, like a swim-based model, to evaluate those more complex outlet designs. So confidence summary. So this table kind of just summarizes what parameters do we feel really good about. We do a great job of calculating which parameters are we a little less certain about. Just again, we've talked about this. It's really that the sediment loading and how that impacts bathymetric storage. Those are very often going to be based on design assumptions, and we need to make sure that we are considering those. So with some of those uncertainties, how do we actually design the pond? Well, that's where the kind of art of stormwater pond design comes in that that's where your experience in identifying reference ponds, identifying ponds that have worked well in similar geographies starts coming in to help you fill in the gaps to say, am I worried that I've under-designed or over-designed this pond? But again, because we're going to be informed by imperfect data, sometimes we have to be comfortable with a certain amount of uncertainty related to elements of pond design. So if only it were that easy, right? This is just the basic, how do we actually do engineering and design of these different elements? There's a lot of other stuff that comes into play when we are designing a pond. I can't get into all of them, but the things that come to mind, right, are, I would say, external factors like permitting considerations, but then there's also internal factors that are kind of competing interests in pond design. For example, if I need a safety bench, that's going to eat into my total supplied bathymetric volume. So there's always a balance of both internal factors and external factors. Just to provide a quick example of this, we can see here we've got a sort of hypothetical situation. We can imagine a city client has said, okay, we've got this problem with this pond. We've got some routine flooding that's happening out here. We're concerned about the water quality. So an engineer will come in and say, I've got this great concept. We're going to put in a forebay. We're going to expand the bathymetric storage volume to prevent the amount of sediment management that needs to be done in the future. And I'm going to expand that whole area to the north, and I'm going to make that an awesome flood detention area to hopefully offset some of that flooding that we've been seeing in the past. So once that's great from a conceptual level, once you start getting into 10 and 30 and 50% design, other things start coming into play. For example, Parks came in and said, yeah, that northern part, that's actually going to be used for a future design project for the park. So that's kind of just a no-go. City's interested in putting a path through this live storage area. That's going to reduce, the amount of live storage we can provide. Watershed district's got some concerns that we still need to talk to them to see if we need a wetland buffer on this expanded footprint. It's a historic wetland, so we're not going to be able to expand the bathymetric storage. We can only remove the accumulated sediments. It's kind of a bummer, but and the sediment's contaminated. So we're going to have to do TLCP testing and figure out, is this hazardous waste? And that could be a problem. Forebay, kind of partially within the wetland delineation. We're still talking to the LGU about that. They might require, offsetting. Do we even need a forebay? That's kind of a area of ongoing research. We'll have to talk to the research council about that and see if that's something that we need to do. We've got FISP passage issues related to carp, easement, access issues. We're not going to be able to get routine access to that forebay. There's downstream flood impacts, and the homeowners are all very upset about this project. So these are all the things that we have to deal with as engineers when we're designing a pond. So this is just kind of a word map of different things that we're thinking about and that often come up in stormwater pond design. Just to summarize this quickly, some of these things are just going to be in direct conflict. So when we have design goals that are in direct conflict, you have to compromise and you have to coordinate. And that's why, all partners involved are always going to appreciate super early coordination, and they're going to, appreciate understanding that this is a shared goal. Right? We're all trying to do our best to make the most of this pond or make the most of this project, and how do we work together to achieve those goals? So achieving those goals often requires innovation. So just a couple examples here, I'll just kind of fly through. We've already kind of heard about ALCS applications. This is where we've got controlled outlets that respond to forecasted weather events. So maybe we can draw down that pond ahead of a stormwater event. Maybe we can reduce that outlet after a rainfall event to improve the detention time in that pond. So again, just kind of doing more with a limited footprint is kind of one of the ideas there. Targeting dissolved phosphorus. We've talked a little bit about that in terms of Ross was mentioning, alum treatments to do the same sort of thing. You can also, in this situation, we've, designed a iron-enhanced sand filter bench that when the pond bounces, it accesses the filter bench, and you get a little dissolved phosphorus removal in that bench. So that felt really innovative when we were working on that 12 years ago, but I think this is getting sort of implemented a lot more often. So it's cool to see those types of projects happening more often. This is a cool example project where you had a pond that was really short-circuiting, a topic we haven't even talked about, another really important consideration. So this is one where a permanent silt curtain was put in to force a more sort of circuitous route of flow moving through that pond to increase settling time. So just another kind of interesting application. And in terms of responding to research, how is engineering and design responding to research? One thing that we're really thinking about a lot as it relates to emerging research that we've talked about today is controlling that internal loading. We know a lot of ways to do that, right? Alum treatments, and in this case, we're seeing they're spraying spent lime in. There's iron treatments. Maybe you put on the ice before it melts. A lot of different ways to do that, but I think an important consideration is how to make those projects as seamless as possible. And some of that is potentially trying to reduce the regulatory burden of doing those types of projects, figuring out ways to be more mobile so we can actually get into those types of projects quickly. But wind action, that's another thing we've talked about today, and that's on a given pond design project, when you're going in and doing maybe removing accumulated sediment, maybe let's also do some clearing and grubbing to kind of increase the wind action going across that pond. And of course, there's lots of really interesting and great ways we have to utilize large data sets to get us looking at the ponds where doing this sort of management and improvement matters most. That's kind of another emerging area of research and application. So again, we need your help. This is something that as we continue to design ponds, we just are so appreciative of the work that researchers do. And again, I know this is always the goal, is to go from research and take it into actually applicable design guidance, and we're always kind of working towards that. But your ideas and thoughts are greatly appreciated, and we'll be really interested to hear more during group discussions on how we can be responsive. So, yeah, with that, I'll just skip over this slide, put my contact information up. But yeah, thank you very much, and I think we've got a really great presentation follow-up from Brian that Keith will give us more information about. So.
Our next speaker is Brian Beck. He will be talking about reconciling what was designed and built to what's in the ground. This finishes out our session. It's a perfect ending for today. Thank you.
All right. Let's see if this comes up. No, thank you so much for having me. Yeah, that was a perfect transition to what I want to talk about. Thank you, Mike. So what I'm going to be talking about today is reconciling, what the pond is, what the goals were, what the design was, and lastly, reality. And so I think it's really exciting, and I think it's an opportunity-rich environment to present in. So I'm from Minnehaha Creek Watershed District. Like many people here, we have ponds, and like a city, a watershed district, you own ponds, and so you either are building them or you have to figure out how effective those ponds are and what you do with them moving forward. And so the concept is deceptively simple, but also incredibly complicated. At a high level, you have what we've talked a lot about, which is what's coming into the pond. That's the wash-off, or runoff from your watershed. Ideally, that sediment in the water comes through your pond, settles out, and your outflow is cleaner than the water that came in. Although we know it's a little bit more complicated than that. You have some potentially internal loading. You don't know what the particle size is. A lot of different factors can make that complicated and difficult to understand. And so as groups of scientists and engineers, we need to figure out what's going on in each one of these ponds so we can understand how we can move forward and make them as effective as possible. But that's a lot of times a very scary proposition for different agencies to do, because, for example, we collect our inlet concentrations, and ideally we have lower concentrations at the outlet. But what's been presented already once or twice is that sometimes the concentrations are the same. Maybe they're relatively similar. That's a scary presentation to give to your board of managers or city council, to say, we spent all this money and now it's not performing as we expected. What if the concentrations are higher at the outlet? That's also really scary thing to say out loud in front of people. Being the bearer of bad news is never fun. And so I think one thing, and I think a lot of the other presentations did a really great job at talking about this, is it's a little bit more complicated, and the pond itself is only one piece of the overall puzzle. And so there's some questions that I like to ask myself when I go out and do this data collection, because I think that the story is a lot more rich than just what's going on in the pond. And so one of them is, what were the assumptions for inlet concentrations and flow? That's a lot of what the last presentation just talked about, whether or not there was complex modeling, whether there was continuous understanding of the system, what model was used, what were the assumptions in that model. Was it a simpler model, like where it doesn't really understand variability, or maybe the land use isn't accurate? Whatever it was, there's assumptions that went into that design, and understanding what those are really, really important. what were the original goals of that pond? Maybe it wasn't to treat a certain pollutant that you actually are concerned about now, and that's different 30 years later. So understanding what the original purpose of that pond was is also really, really important. And lastly, have there been changes in the landscape? Maybe it used to be an agricultural area with really low runoff, and now you have a system that's been developed, and this pond now is receiving much higher flow, lower residence time, and the pond now has less ability to settle out phosphorus. So all of those pieces of information are really, really important. And so kind of getting further into that is the assumptions for the inlet, or what you get for runoff, are really, really important. And as Mike said, a lot of times we're relying solely on modeling. The complexity of that modeling really changes. This is an example. There's a pond at the outlet here. We had P8, and even if you have a P8 model, sometimes you don't know all the storage upstream of that system. So are we assuming that there's phosphorus taken out prior to going to this pond? Or is it just saying, oh, all the runoff just reaches the pond? And so those different things going into it really, really make a difference with the performance of that pond. In addition, is that model calibrated? Was there data ever collected for that system? In addition, was it collected at that very location? Where's the pond, or was that model calibrated globally for a whole area? So all of these things make it much more complex. What were the original design goals? I kind of talked a little bit about this, but some ponds may not have a water quality focus, so they're going to be designed differently than maybe if it's just for storage or something different than what you're really looking for. And lastly, in a lot of our watersheds, I alluded to this. This is an example of a watershed that's actively developing, and so right now it's currently heavily agricultural. We have a pond at the outlet, but we know over time it's going to become more urban. So is this pond going to perform exactly the same as it does today, or when it was designed 30 years ago, or 20 years ago, I guess? And so those things compound as well. So for example, let's just say, the upstream change, or the upstream conditions change. Well, that's important because it's going to change the assumptions for volume. In addition, it's likely going to change what our goals for that pond are. And even beyond just the system change, maybe a downstream water body was listed as impaired, so you actually want to get higher reductions. And so maybe there's no other places to put a pond, so you know this pond is really important to maximize your reductions for this whole subwatershed. So it's not just what are the constraints of the pond, but it's also how does the system change, and how do your needs change as an organization as we're trying to manage our finite resources and putting things in the landscape. And so kind of with that at a high level, I wanted to dive into just a specific example just to show that these things really can be done. We can monitor these things, and we can really understand how to improve our systems. So going into, we have a subwatershed, Long Lake Creek subwatershed. It's in the north central part of Minnehaha Creek. We have a pond that was built in 1998, and it receives drainage from a pretty large area that drains to Long Lake, which is impaired for nutrients. This is just the project design. So the goal was to have a 16% reduction, which is actually pretty small, but this was before having impaired water body downstream of it. So I don't know the person that designed it in 1998, but I think 16% is a relatively low reduction goal. It was monitored subsequently after it was built, and what that monitoring showed, said it was only 6% reduction, which is pretty disappointing. And so how do you communicate that information, and why is that happening? And as we dug into this, when I started, different folks at the district said, this pond isn't working. all the data shows it's not working. And so we said, well, why don't we go out? Because what we noticed was in the monitoring data was that there was no storm samplers. It was only grab samples, so it was just base flow. And so it's not surprising that in an area with a lot of storage, that the base flow concentrations are actually pretty good. So we went out and put out storm samplers at the inlet and outlet to understand. And what we found out was actually concentrations are much higher at the inlet than originally expected. And so we were getting a reasonable reduction of 40%. And so that was simultaneously good news and bad news in that the concentrations are higher at the outlet than we really anticipated. But what this told us was there's a lot of meat on the bone at this site to reduce phosphorus. More information that we had, which we went and monitored upstream in addition to the pond, was that the primary phosphorus source is through ravine erosion, which isn't characterized in a lot of the models that we used. And so it's almost exclusively particulate phosphorus and very little dissolved phosphorus. So what that told us is this site is ideal for not only settling phosphorus during those high flow events, but also one thing that we could do is put just a sand filter bench at the outlet to catch a lot of the particles that are going through in kind of lower flow and high flow situations. So with that being said, not only did our understanding of the pond system change, but over that time, an impairment was listed in addition to a TMDL was produced. And so what that said was we have, standard TMDL, we have watershed load reductions, internal load reductions, upstream load reductions. And so we worked with an engineer to say, okay, if this is our new understanding of this system, what can we do to maximize the effectiveness of this pond? And so what we identified was we could get an additional 40 pounds of reduction for the system based on the refined understanding that we have of the system. And so that was really, really important because now we actually could take a pretty big bite into that watershed reduction, which I think we all know finding watershed projects can be really hard. And not just finding them, but also getting them in the ground can be even harder. And so we actually built this sand filter over this last winter, and so it's going in. We're going to monitor the effectiveness of it coming up, and we're really excited to be moving the needle on a system, not only just from the pond that we currently had, but also finding a relatively inexpensive way to improve water quality for our impaired water bodies. And so with all that, I think just looking into why we would monitor, why we would characterize what's going on, but more importantly, how do we put that pond in context of the system around it and how things are changing, I think is as important as what's happening in that pond itself. And so understanding those original assumptions is really, really important, because if you don't understand why that pond was put there, how it was designed, why it was designed the way it was, it's really difficult to understand how you can improve your system. And more importantly, a lot of times the assumptions that were there originally may have changed over time, or maybe more importantly, your goals have changed for that system over time. So it really provides an opportunity-rich environment of finding ways to improve systems that you already own. I think another thing that we found is really important is understanding why the measured load reductions or concentrations are different from expectations, because usually those differences aren't just, I think it's easy to say, well, look, this pond isn't effective, but understanding why it's not effective can make a retrofit or an additional project really attractive, because now you actually understand the system versus having to really rely on a lot of assumptions. And so I think the last piece is gaining a deeper understanding of how the pond is working really can lead to potential additional load reductions. And I know monitoring these systems can be exceptionally hard. I always think of running ISCOs like raising a temperamental child. They never work how you want them to, and they're always misbehaving, but it's worth it almost every time. You really never regret doing it, and I think just as a community of engineers and scientists who are trying to do the best we can, we can do hard things, as I tell my kids, even if they are ISCOs, and real children. But I think the most important thing is, it's worth doing almost every time, and I think, we can do a lot of big things together. So I want to thank everybody, and I guess that's it.
Go away, Brian.
Yeah, don't go away.